In this problem, there's a 10 centimeter long tube, half of which is filled with water and half of which is filled with D2O. The mass concentration and molar concentration of these materials is given. The molar concentration of water and the molar concentration of deuterated water is about the same, at about 55.5 thousand moles per cubic meter. So because these molar concentrations are about the same, this means that the number of moles of H2O diffusing into the side with deuterated water and the moles of D2O flowing into the side of H2O in the tube will be about the same. So the molar fluxes will be equal and opposite. This means that the net molar flux of the tube will be equal to 0. This means that when we write out the molar fluxes for the individual components, these two terms with net molar flux can be canceled out. This means that for each term, the molar flux is equal to the molar diffusive flux. So since the molar fluxes of these components are equal and opposite, this means that the molar diffusive fluxes are also equal and opposite. For mass flux, the density of water and the density of D2O are not equal, meaning that the individual mass fluxes will not cancel each other out, so there will be a net mass flux. To calculate this mass flux, we first look at the molar flux of each individual component. So for example, when looking at the mass flux or the molar flux of water, this is equal to the concentration of water times the velocity of water. At the point where there is maximum molar diffusive flux of 2.78, the concentration of water will be this molar concentration, so about 55,000 or 55.5 thousand moles per cubic meter, times the velocity of water. So the velocity of water is 5.009 times 10 to the negative fifth. This velocity can then be used to calculate the mass flux of the water. So mass concentration of water times the velocity of water equal 0.05 kilograms per square meters per second. We can then use this velocity to also calculate the mass flux of D2O. Because since the molar fluxes are equal and opposite, they'll also have equal and opposite velocities. So the mass flux of D2O will be 0.0556. The total mass flux will be the sum of the individual mass fluxes. Oh, this should be opposite. So the sum of these two fluxes will equal the total mass flux, 0.0056 kilograms per square meters per second, corresponding with that maximum molar diffusive flux of 2.78. So this is the answer to number 1. The driving force can be calculated by relating the molar diffusive flux to the driving force using the Stefan-Maxwell relation. Molar diffusive flux is given at 2.78. The overall concentration will be 55.5 thousand. The diffusivity constant for liquids is 10 to the negative 9th. And then we can solve for driving force. So the driving force, when solved using this equation, will equal 5 times 10 to the 4th, which is the answer to question 2. When looking at the graphs, for mass concentration, at the initial point, when the liquids have just first started diffusing, each one will start at its initial mass concentration. So for water, 1,000, for deuterated water, 1,110. They'll stay at this concentration until they reach the interface and then drop to 0. When the liquids have fully diffused, their concentration will be uniform across the tube. So for water, this will be around 500 kilograms per cubic meter, and for D2O, because it's slightly more dense, it'll be a little bit higher than that. And then while it's diffusing, the graphs will be somewhere in between here. Similarly, for the molar concentration, at the initial point before the liquids have had much time to diffuse, they'll be at their initial concentrations until they reach the interface and then drop to 0. Once the liquids have had time to completely diffuse, their molar concentration will be uniform across the tube. So both of them will be at about half that initial concentration of 55.5 thousand moles per cubic meter. For molar diffusive flux, initially right up until we reach the interface, there's not going to be any molar diffusive flux because there's no concentration gradient, so there can't be any driving force to produce a molar diffusive flux. So for example, for water, it'll be 0, 0, 0, 0, 0 until it reaches the interface where we have our maximum molar diffusive flux of 2.78, and then it'll go back down to 0. And the molar diffusive fluxes are going in the opposite direction, so they should be equal and opposite to each other. Once the liquids have had time to fully diffuse, there will no longer be any molar diffusive flux because the liquids will no longer be diffusing. So both molar fluxes will be at 0. Molar diffusive fluxes will be at 0. And then while it's diffusing, the graph will be somewhere in between. So there will still be a molar diffusive flux, but it won't be as great as it was originally. For net mass flux, initially, all of the mass flux will be happening at the interface where the liquids are interacting. So it'll go from 0 to negative, there should be negative over here earlier, negative 0.0056, and then back to 0. When the liquids have fully diffused, there'll be no more mass flux, so the mass flux of the system will be 0. And then while the liquids are still diffusing, the graph will be somewhere in between. Oh, and then up here, this line, I drew this wrong originally, so I just scratched that. So yeah.